Last little bit of an idea that we look at is symmetry of the shape. And we've already seen this idea, of course. We know even functions. When we're integrating even functions, remember even functions is function negative x equals function x, symmetry about the y-axis. And we've seen that, well, if I want to go from minus a to a, I could say twice 0 to a. Now, we could use this idea, even if it's not symmetric about the origin. If we notice it's symmetric about another point, so it might be a function that's been shifted a certain way. So if we notice there is some sort of horizontal shift and it's symmetric about some other line, x equals whatever, in this case I've said x equals c, then it must be true that, well, let's say we've moved it to c, then a units before c, if I was integrating from that to a units after c, would be twice from c to c plus a, because you've still got that symmetry. Now, I don't know if that's ever going to happen. How useful is it with even functions? Because you're still something. I mean, the beauty of it with the even function was that you're substituting 0 in. So here, does it make it any easier? You're still substituting a number in. Maybe it's not that useful. However, the odd one could be. Function negative x to negative function x. And remember, we had the rotational symmetry, which meant from minus a to a, it was 0. So if you notice that rotational symmetry, this time, well, if you have a horizontal shift, it could be useful. Because if you've got that rotational symmetry about, again, we'll use c, then I know if I'm integrating from c before a to c after a, sorry, a after c, oh, it's the same actually, isn't it? But anyway, that answer would have to be 0. Well, the same idea, because we've got our odd function and we've just shifted it across. Again, it probably is a very rare question, but you never know. Could be something that comes in handy. Here's a third little idea. If you integrate from 0 to a of a function, it's exactly the same as if you integrate from 0 to a of a minus x, function a minus x. Because basically, if you did a substitution, you could prove that to be true. Now, here we go. Whoop. So there's the integral from 0 to a function a minus x. So let's say I did the substitution, u equals a minus x. So du equals minus dx. I've got to change my limits. When x equals 0, u is a. When x is a, u is 0. So the limits flip around, and I've got minus function u du. Well, I can fix up the minus by swapping the limits, but then as we know, when it's a definite integral, the pronumerals are relevant. I can put any pronumeral I like in there. And so it's the same as function x dx. Also, keep this in mind. Odd times odd, even. Odd times even, odd. Even times even, even. So if you have got a product of functions, then again, you could use symmetry ideas. If you notice one function is odd, one function is even, and you're, I don't know, integrating from minus 3 to 3, and you go, hang on a sec, ooh, odd times even, that's odd. Symmetry, oh, that integral must be 0. Save yourself some time. Such as this one, sine cubed. Sine cubed. Well, we know sine x is an odd function. So sine times sine times sine. That's odd times odd times odd. Well, odd times odd was, and then even times odd. So sine cubed must be an odd function. So I don't have to waste time using techniques. Be surprised how many people do. I can just say, oh, hang on a sec, I know that's an odd function. So it's just equal to 0. This is where that idea of function a minus x is useful. I can't expand this out because I've got 1 minus x to the power of a half. How do I do that? Well, I can't. So I'll change the integration. Everywhere there's an x, I'll replace it with 1 minus x. And now I've got something I can expand out because the square root now is just on one term, just the x. So if I expand that out, it's just x to the power of a half minus 2x to the 3 on 2, x to the 5 on 2, add 1 to the power over the power, subbing in, we get an answer. Okay? Now, the reason that one worked is because look at the question. It was 1 minus x, but I was going up to 1. So when I substituted in the 1 minus x, the 1's cancelled, it became nice. But if you do notice things like that, then hang on a sec, look, this limit matches that, maybe this could be a useful idea. Okay, improper integrals. Okay. Now, that's when we want to integrate something, but it doesn't exist at one of the endpoints of one of the limits. So it might be, say, for instance, say I was doing my hyperbola over there and I wanted to integrate from 0 to 1. Like, I can't sub-zero in because it doesn't exist there. So we don't actually use 0, we use limits. We say, well, what's the limit as it's approaching 0 then? And that'll give us an idea. And so here it is, 0 to 1 of dx on x. I'd say, well, look, I can't do that. So what I'm going to do is I'm going to find the limit as n approaches 0, the integral from n to 1. That I can do because n's now just a pronumeral. So integrate, we get a log. Sub in, we get minus log n. Now as n approaches 0, what does my log function approach? Well, it's undefined. So in this particular one, I can't find that integral. It is still going to be undefined. No good. But let's have a look at this one. If I went from 1 to infinity of xe to the minus x squared, and that one goes asymptotic, you might remember, to the x-axis, I think it is, isn't it? But anyway, we're going off to infinity. How on earth can we work out this? It's infinite. How do I get a volume? So same idea. Well, I can't sub infinity in. So let's go limit as n approaches infinity, 1 to n of xe to the minus x squared. I've got derivative e to some function. So that will integrate to be minus half e to the minus x squared. So e to the minus n squared. Now this one I can work out. Because what's the limit as n approaches infinity of e to the power of negative n squared? Well, that's going to be 0. Because that's our exponential coming down this way. So it does actually have a value. 1 on 2e. I can find that improper integral. Now, inequalities and area. Very useful. Okay? So the idea is this. You've got your graph, and you know that I've got 3 functions here, g, f, and h. If I know g is always below f, is always below h, so there's 3 things on your graph, then obviously the area under those must be also in that same order. So here's a 2009 question. Question 8b, end of the paper. So supposedly tricky. So n's a positive integer greater than 1. There's our curve y equals 1 on x. They've drawn a little rectangle there from n minus 1 to n. We need to show this beautiful expression. E to the power of minus n on n minus 1 is less than 1 minus 1 on n to the power of n is less than e to the minus 1. Okay. Well, what I know, back on that diagram, is the area of the inner rectangle, so that was the smaller rectangle, must be less than the area under the curve, must be less than the area of the outer rectangle. So I can trap the area of that integral in between the area of those 2 rectangles. So area of the small rectangle would be 1 on n times 1. The area of the larger rectangle would be 1 on n minus 1 times 1. And of course, area under the curve would just be the integral of n minus 1 to n of dx on x. So working that out, we have 1 on n log x when we integrate. We've got to substitute in, of course. So let's do that. And we get log n on n minus 1. Now, that's not quite what they wanted us to prove. So let's play around. Okay, I've multiplied everything by n. So 1 is less than n log n on n minus 1, which is less than now n on n minus 1. I've brought the power into the log, using my log laws. I now have n on n minus 1 to the power of n. Now, of course, to undo a log, I exponentialize. But because I know my exponential curve is increasing, as my numbers are getting bigger, then again the area under the curve is still going to be in that order. So it is fair, we can say this, E therefore, that inequality must be preserved because it is continually getting bigger as we go from left to right. So E is less than n on n minus 1 to the power of n, which is less than E n on n minus 1. Well, I think we're getting close to what they want. I've turned both sides, or everything, all 3, upside down. And remember, when you turn a fraction upside down in an inequality, the inequality sign changes. So I now have 1 on E is greater than, n minus 1 on n to the power of n, is greater than 1 on e to the n on n minus 1. Let's make those inequality signs look right. So the 1 on e has become e to the minus 1. Here, it's e to the minus n on n minus 1, as you can see there. And there's our 1 minus 1 on n. I've just broken up our fraction into 2 parts there. And that's what we wanted to prove. Because e to the x is continually increasing. Right? So what we're saying is if 1 is less than the log, and it's less than, so we know those particular x values that we're substituting into them are getting bigger. But as e to the x is getting bigger as we go there, because the power that we're substituting is getting bigger, then we must be getting bigger y values as we go along. Patel, Cambridge. Now, notice in the Cambridge, we talked about the idea a minus x. They've used 2a minus x. Still the same idea. Oh, the 100.